Okay, hello everyone, and welcome to our monthly PCAST talk series. This month we actually have a special talk, so we've got two talks this month. So we're going to be coming back again at the end of September. Just a few updates here from the PRIMA projects. We're very excited later this month to have the GEO General Observer Book Volume 2 coming out. We had more than 120 submissions, more than 400 authors from 34 countries. It's been a really spectacular turnout and really lots of great science ideas. We want to say again another special thank you to everyone who participated in submitting these cases. We also have other news on the science front that we had the PRIMA special issue just published in JWST. So these papers are now all in the archive. So they went up on September 3rd. So you can go find them. And these are papers both on science that you can use PRIMA for, as well as sort of the technological underpinnings of this project. Our next talk is a slight change. So as I said, we have another talk this month, September 22nd. This is going to be Edgar Vidal from Tufts University, and he's also going to be talking about some JWST results, so JWST MIRI, looking at dust-obscured AGN and paving the way for science with PRIMA. So today, of course, we have Klaus Pontoppidan from JPL, and so he's going to be talking about the origins of planetary atmospheres, both the amazing things that can be done right now with JWST and how that's sort of really greatly improving our view of these sources, and then what PRIMA can uniquely contribute in the far infrared in the future. So go ahead, Klaus, and thank you.
All right, thanks, Betsy. See. Can you see my slide?
Yes, looks good.
All right, great. Thanks so much. Yeah, so thanks everyone for joining. I'm really happy to be able to talk about the science and its relation to what PRIMA is going to do. The talk is entitled "The Origins of Planetary Atmospheres." There's a fair amount of background story here. I'll talk about and summarize a fair amount of JWST results, but it's really because they lead directly into a lot of the stuff that PRIMA is going to do and drives a lot of the design of certain parts of PRIMA and PRIMA's instrumentation. So I want to start out with the modified Drake equation, because I think it really goes to the core of what we're trying to do here, right? Of course, the Drake equation is just a summary of probabilities that all lead to the probability of, in the modified case here, of that a planet exists and will have life, right? And so they're the classical, just the fraction of stars with a planet, and a fraction of those that are in a habitable zone. But in particular, I want to draw attention to the third factor in the equation here, right? And that is the fraction of these planets that have the right chemical makeup of carbon, hydrogen, nitrogen, oxygen, and so on, of the elements that are needed to produce life as we know it, right? You can think of this as a kind of chemical habitability. And a lot of what we're trying to do is to try and understand that fraction, right? Because it is, we think, so fundamental to the probability of finding life. And it's one that I think traditionally has maybe not been looked at too closely, but now it's becoming something that is a very active area of research, right? And so what we're really asking here is if the Earth and the solar system is really a common configuration, but not just in terms of dynamics, size of planets, temperature of its surface, but the chemical ingredients, right? And so processes that lead to that, are those common? It's a question like, how do we get the chemical makeup of a planet in the habitable zone, right? Do the initial conditions for protoplanetary chemistry matter? I mean, I think the answer to this is obviously yes. The water, the other light volatile elements that we have on Earth that led to life obviously came from the protoplanetary disk out of which the solar nebula, the protoplanetary disk out of which the Earth formed. This would be true for any other planet. But how does it matter? And so in terms of how does it matter, I think we can ask what is the relative distribution of the CHNOPS elements that are available to planets, and are they really always the same, or are they not, right? And if they're not, then in what ways? And then it becomes really interesting if the answer to that is no. So this is one of my favorite plots from the solar nebula, from the solar system, that kind of really illustrates this. And so the abundant, this is what it shows here, is the abundance of elements in the Earth, specifically the Earth's mantle, and the abundance of those same elements in the sun, right? And if they fall on this dashed white line, it means that the relative abundance in the Earth is not depleted relative to that of its parent stars, the sun. And if the points are below the line, it means that they're depleted. So obviously some things like oxygen is depleted. Famously, carbon is depleted by about 3 orders of magnitude compared to what the sun has, and nitrogen is depleted by up to 6 orders of magnitude in the Earth's mantle. And the reason for that is that the delivery of these volatile elements depends on their carrier, depends on their molecular carrier. So if the element is carried in some molecules, those may be more or less volatile. The Earth formed out of solid material, and so if the molecular carrier was too volatile to exist in solid material where the Earth formed, it wouldn't have been incorporated. And so there's a very direct link to the protoplanetary chemistry. And so that is what we're really interested in observing, not just from the archaeological evidence in our own solar system, but really around other stars. And for that, we have to observe protoplanetary chemistry in young systems around young stars. Of course, we can approach this from another side as well, namely by looking at the makeup of exoplanets, exoplanetary atmospheres in particular, right? We get this beautiful data now from JWST showing these beautiful transmission spectra that tells us about the abundance, and in particular the relative abundance of molecular carriers of various of these important elements. Things like water, carbon dioxide, ammonia is a carrier of nitrogen, sulfur dioxide in this case, a carrier of sulfur. And you can put all those together and get some idea of the relative abundance, say, for example, famously of carbon to oxygen in exoplanetary atmospheres, and you can try and infer something about the chemical makeup of the disk out of which that planet formed, and that is being done frequently and routinely in analysis of exoplanetary chemistry. There are issues with that, though, right? One, and there's a number of them detailed here. Planets have the unfortunate property of having clouds often and hazes, and that limits sensitivity to molecular features. A lot of folks are working really hard on trying to run retrieval models, right, that take these spectra and try to measure the relative abundances, particular carbon and oxygen, and measure the precision with which those can be known based on, say, a JWST spectrum of a planet. And we're finding that a lot of these planets are degenerate in both the metallicity and the carbon to oxygen ratio in many cases, right? That the data are just not quite, they don't have quite the enough detail, quite the right amount of detail to get very precise measurements of these, right? So that sort of limits our ability to interpret what we see. We know that we have significant atmospheric loss in terrestrial planets. So if you go down in mass to rocky planets, we're interested in their makeup. So there's significant atmospheric loss, and those are the easiest to observe. So those are the ones that orbit M dwarfs. And so because of that history in between their formation and what we see today, it's not so easy to infer what their original makeup was in these kind of secondary atmospheres with loss. And then low number statistics, right? So even JWST makes beautiful observations, but the numbers are relatively low. Even a future observatory like Habitable Worlds Observatory will have relatively low number statistics, particularly for terrestrial planet atmospheres. And so these are all sort of limitations that lead us to consider observing things when planets when they're actually forming, in particular the environments in which they form. So this is where we get to observations of protoplanetary disks. So as we know, planets form in protoplanetary disks. Here's one of the famous images of dust in a protoplanetary disk is observed with ALMA at high spatial resolution. So one of the things I always want to point out, though, is that when we interpret observations from something like ALMA, we have to caution ourselves in that they are often biased to the outer disks, relatively large radii, and so this is just an example that compares this image of a disk with where important structures in the disk is, in particular the snow lines, right? So there's a water snow line, which exists at relatively high temperatures, right? So the water snow line being the place in the disk where temperatures are such that water can transition from solid to a gas phase. Somewhat larger radii, there's a CO2 snow line, and an even larger radii, there's a CO snow line here. And at the bottom, you can just for comparison, I've indicated the orbits of planets in our own solar system. And so what you see is, if you're interested in things that happen in the terrestrial zone, where terrestrial planets form, that'll happen, inside the water snow line. That is well within a beam of ALMA here, even at the highest spatial resolution. And even for giant planets, most of the action happens within that beam or within just a couple of beams here. There's some bias in studies of these disks where they have these beautiful rings. It turns out that those are the largest, most massive disks, and have been selected that way for initial studies with ALMA. More typical disks don't quite look like this. They're not quite as impressive. They're more compact. And those may be more representative of what a young solar nebula once looked like. So here's another way of considering that point. So what it's showing here is just a classical plot of known planets with a semi-major axis on the x-axis and the mass on the y-axis, and Earth is indicated with a nice red star here. And then the red box to the right, that is the area where we can have resolved line imaging with ALMA, right? So where we can resolve molecular lines to tell us something about the chemical makeup of disks. And that resolved line imaging with ALMA really doesn't cover where most planets exist, or at least the ones that are known exist today, right? So the planet-forming region is probably inside where we can image things at radio wavelengths. We do know that planets don't stay where they form, but they typically tend to move inwards. And so here's just one example of a simulation of planet formation, just to give an idea of where we think most planets form and where they take up most of their chemical matter initially. And as you see here, it's most of them. You can see the distribution on the right of birth lines of planets, that it happens sort of within 5 AU or so, which is just inside or just outside or just around the water snow line in this case here. And this is because the formation of giant planets is really catalyzed by the local abundance of solids. The more solids are there, the easier it is for the disk to form a planetary core that is massive enough to attract a large atmosphere that leads to the formation of a giant planet. And the solid mass is biggest in a disk just outside the snow line, where a lot of the mass is coming from ice rather than from rock, right? And so that tends to catalyze planet formation there. And that's sort of still is the sort of predominant model writ large of how and where planets form. So that's the area we're really interested in understanding the chemistry in planet forming disks. So say within a few AU or maybe out to about 10 AU. So here's a schematic of all the things that is happening there. We really made great strides and progress in the past a decade or two, and certainly within the past few years, theoretically in understanding what goes on here. And so now we know that the snow line is not a simple structure. It's sort of a curved structure. You can see that as sort of a green sheet here in this schematic. So we have a snow line, and then inside that we have water vapor. There's a lot of mixing going on, right? So ice will sublimate from the midplane, and then the vapor will be mixed up. And where we're able to observe the chemical makeup is not typically in this region in the midplane, because the disks are highly optically thick. We observe it from the surface. So we're seeing sort of the upper layer of this where the material has been mixed up through vertical mixing. There's also an inwards arrow here. That's where you can see it's called pebble flux. And we're starting to understand that is a really critical mechanism in disks for shaping their chemistry. Pebble flux is the inwards drift of pebbles, so that is solid particles that have grown to sizes of, say, a millimeter or centimeter, through hydrodynamics in disks. Grains or particles of such size tend to drift inwards against the pressure gradient. And the reason they do that is because of the gas in disks orbit at slightly sub-Keplerian velocities because they're supported by pressure against the pressure gradient. They're not orbiting freely just from gravity. They have a little bit of pressure from the inside of the disk where pressure is higher, so they can orbit at somewhat slower velocity. It means a particle in that size will experience a bit of a headwind, which leads it to lose angular momentum and drift inwards. And in extreme cases, on a very simplified disk, this drift happens very efficiently, such that the disk could lose its solid component within just a few hundred years, out to 10 or 20 AU. So you can have disks that are depleted very quickly in solids, including of ices. However, if you have a pressure bump, if you don't have a uniform pressure gradient, you can also concentrate material, and that's something we think might happen also near the snow line, and that can also catalyze planet formation. Right? So we have these processes that lead to the bulk transport of icy material from the outer disk into the inner disk, and that can locally dramatically change the chemical makeup. For example, if you have very water-rich or water ice-rich pebbles, if they drift and concentrate in a certain part of the disk, you can greatly increase the amount of oxygen there, and that can change, for example, the carbon to oxygen ratio. So one way to look at that is to the more creating this kind of more global evolutionary models here. And so there's a kind of a cartoon description of what might happen in a disk. So here you have just a function of time. You have the inner disk vapor mass. And so through this kind of pebble drift, what you'll have is, as the disk is very young, you can have a very efficient inwards drift. It means that you have an enrichment over time of the water vapor mass. Eventually, you essentially deplete your disk out to a certain radius of water ice, or these pebbles that can drift inwards. There's only a limited reservoir of those. And so when you reach that point where you're starting to deplete the disk, you have a depletion onto the star of the inner disk vapor, and no more supply of ices coming from outside, and then you end up with a depletion over time, right? So you're peaking the water vapor mass at a certain time, and then as the disk gets old, you might see the disappearance or the depletion of water. And so depending on when you're forming your planetary cores, on this timeline, you can imagine how you can create very different planetary compositions. And so you have these multiple competing timescales that probably operate, and that's something that you can look for observationally. All right, so we talked about ALMA, we talked about where planets are forming, we talked about the areas that we'd want to try to observe protoplanetary chemistry. Another thing we'd want to do when we're doing this experiment is we'd like to measure the entire inventory of a certain element, right? So if you want to measure the entire, for example, carbon to oxygen ratio, you really need to account for all the carbon and all the oxygen. So we have to look for not just molecular tracers, we have to look for the bulk tracer, right? So if most of the oxygen is in silicates and water, we need to observe both the silicate and the water, for example. If most of the carbon is in CO2, for example, or CO, we need to observe all the CO and CO2. And so here's just one instance of a model of where those bulk carry, what the bulk mass is of gas on the left and of the solids on the right. And I'm just going to mark here the ones of the bulk carriers that are primarily traced in the infrared, right? And so as you see, it's actually most of them. A famous thing is something, for example, like water. Like water is not something that ALMA can observe, at least cannot easily observe. You actually have to see that in the infrared. CO2 is another example that in the ices and the solids, we expect it to be a lot of CO2. That is primarily or only really observed in the infrared. And so radio wavelengths is really not enough to be able to do this kind of experiment. We have to look at the infrared. And so that is a field, observing the protoplanetary, planet-forming chemistry, bulk chemistry in the infrared is something that started maybe 2 decades ago, sort of in earnest at least. And probably the first sort of the first forage into that area was the discovery and observations of the low vibrational bands around 5 micron of carbon monoxide, the fundamental band there. Right? And so that was done from the ground with new sort of relatively high resolution spectroscopic facilities, such as on the VLT and on Keck. And so it's just an example of some of the seminal work here that shows what essentially found was the ubiquity of carbon monoxide, tracing gas at about 1 AU in protoplanetary disks around stars of a variety of masses. Here we're showing some disks around somewhat more massive stars, about Herbig stars around 2 solar masses, but we also found that the same thing holds for disks around solar mass stars. So that was sort of the first indication that, hey, we can actually constrain the planet-forming chemistry using infrared spectroscopy. The next great sort of leap that happened, that was a huge leap, was the launch of Spitzer. And with that, the opening up of mid-infrared spectroscopy, not really at high resolution, really at quite modest resolution, but was enough to demonstrate that CO is not the only molecule we could see here. Most importantly, we could observe water, we could observe CO2, and we could observe various organics, including acetylene, HCN. So those were sort of the key species that were available in the, let's say, in the 10 to 30 micron region. And it was a bit of a surprise when we found these. Yeah, it took a few years actually to realize what we were seeing. So we're seeing these dense forests of many molecular lines that were all blended together because of the relatively low spectral resolving power of the Spitzer spectrometer, the IRS. I remember there was a couple of years at least where folks thought that it was basically noise we were seeing, and we're trying to get rid of it until we realized, hey, you put a water model on top of this, and it's all water. So we found that this kind of molecular emission from inner disks is really common, in some cases nearly ubiquitous. But what we also saw was that there were real chemical differences depending on the stellar mass, the mass of the young star, where in disks around stars with significantly higher masses than the sun, there was not that much chemistry to be seen. These were mostly featureless spectra. We saw things in CO, as I showed before, in the low vibrational band, but we didn't see the water, for example, or so only very little water. Disks around solar mass stars we saw a lot of water, we saw a lot of organics, and there were initial indications as well that disks around really low mass stars, down to the brown dwarf limit, which Spitzer could do just a little bit of it, just sensitivity to do a little bit of, didn't show the water, but showed these very strong organic features. And so already then we were sort of talking about there was sort of a spectral sequence of protoplanetary disk chemistry, but that was as far as we could go back then with Spitzer. It was the data were not quite good enough to really delve deeper into detailed abundances. So here's just another sign of what was going on back then in terms of the relative detection fractions of various molecules. And you can see that typically we would see this kind of molecular emission for maybe about half the disks around solar mass stars or so, and much less around more massive stars. So moving to JWST. There are quite a lot of observing programs now with JWST following up on these first initial results here. So I'm involved in a program that's called JDisks. There's another one called MINDS. These are two big ones, and many other smaller programs. When you put it all together, it adds up to actually quite a lot of JWST time that has been used for this here, because especially the mid-infrared spectrograph MIRI with JWST is a very powerful instrument to do this kind of science. So JDisks is sort of an alliance of many smaller programs. So up until now in cycle 4, we have about 350 hours of observing time, 135 disks. So we're building up these relatively large samples of protoplanetary disk chemistry. What JWST spectra now look like of a range of protoplanetary disks, and so you can get a sense for the incredible richness of what we see here. So we see these dense forests of water lines, and we see organics, we see CO2, we see all the same things we saw with Spitzer, but now we see them in great detail, and we have a solving power that's high enough to separate all the individual lines, and that allow us to analyze them in more detail, in particular to measure their abundances, the temperatures, and other properties. And so that's what we're doing here. So this is one example, an overview paper by Nicola Rolanantham on behalf of the JDIS survey, summarized some of these same properties that we saw with Spitzer. So in terms of detection fraction, now we pretty much always detect water in all the disks. And in many of them, more than half, we detect all the other molecules as well. We can measure the temperature. So we can see sort of on average, the temperature is different for different components. CO2 tends to be cooler than the organics. And this is an indication that the emitting radius, so the radii that emit the emission from CO2, for example, is larger than that of the organics. So we start to see radial stratification of the chemistry in disks, so writ large. In particular, water is something we can look at with some detail. And this is because, again, you saw this amazing forest of hundreds, even thousands of water lines across the mid-infrared. And these lines all trace different temperatures. They have different upper level energies. And so if you make a model, you can see that on the left here, you can on the x-axis, you can see the wavelength of a water line. And on the y-axis, you can show the radius that it traces, right? And so water lines that have lower upper level energies trace cooler gas. And so that gas comes from larger radii. And so that means it traces a wider radii. And so you can see overall, there are water lines that trace hot gas at any wavelength pretty much. But if you want to trace the cooler gas, you typically have to go to longer wavelengths. So overall, if you have a range of wavelengths available, it means that you have access to cooler and cooler water the longer wavelengths you have access to. And so there's a lot of work going on right now in terms of measuring the temperature distribution of the water we see and using that as a proxy for measuring the radial distribution of water masses. And as an example of that to the right here, we can construct the kind of color diagram of water where placing a source or a disk observed with Spitzer in different location of this plot here gives you an idea of how much relatively cool water there is relative to warmer water. Right, and so again, it gives you a proxy for we don't have spatial resolved images, but because we have access to so many water lines, we can get some sort of proxy for the radial distribution of water using this kind of modeling. And so one of the things that has been looked at is, for example, is look for signs of pebble drift, as I mentioned earlier. So one of the things that we're trying to do is to see if there's a correlation between the size of the dust disk, as observed with ALMA, and the amount of cool relative to warm water, right? The idea being that a compact disk, as you see in top left here, has had a very efficient pebble drift, right? So you see all the dust has been concentrated on the inside of the disk through pebble drift, and that would give rise to a lot of water just inside the snow line, just evaporating. That would give rise to a lot of cool water. Whereas a disk that has not experienced much pebble drift, potentially because the inwards drift of pebbles have been disrupted by pressure bumps, that has not had a lot of enrichment just inside the snow line, and so there the water will be relatively hotter. And so there's a lot of indications that that is indeed what you see. So you see the middle plot here. There's some of the very early results found some strong correlations. Later results on the right here, where you start to add more disks with more complex structures. I mean, you get a more complex picture, but we think this is because disks are inherently complex. They have complex radial structure. The pebble drift is a complex story, and so there are confounding factors. And so this is all something that is starting to be worked out with larger samples with James Webb. Another interesting part here, so it's not just water, right, we're looking at other molecules as well. It's a very interesting story potentially being told by CO2. There's a subset of disks that have very high abundances of carbon dioxide and very low apparent abundances of water. And here we think what's going on is that the water in the inner disk has either been depleted or there's been a carve out of the inner material of disks from planet interactions or other things. And the only thing that's left is what you have access to is not the water snow line, but the CO2 snow line of somewhat larger radii. And that gives rise to also an opportunity to see chemistry that becomes in the vapor becomes very, very CO2 rich. And there's a subset of disks like this. The reason I bring this up here is because of the recent JWST observations of one of the interstellar comets, the third one, Atlas here, which is now one of the famous ones here, coming in from another solar system, another stellar system, giving us a glimpse into a chemistry that is not part of the solar nebula in a comet, right? And in this case here, it has an abnormal chemistry compared to solar system comets in that it has a very high CO2 over water ratio. So it's something that actually matches what we see in a subset of disks. And so just an indication of it starting to be able to make these links to interstellar comets to other to protoplanetary disks and protoplanetary disk chemistry writ large. So an exciting result here that I'm looking forward to understanding better. A third thing that we are discovering is the nature of the organic chemistry. And this is always becoming very interesting. So I mentioned that we already saw some indications with Spitzer that the carbon to oxygen chemistry is very different in disks around very low mass stars, right? So down to brown dwarf masses. And that has been confirmed and greatly expanded on with James Webb due to the high sensitivity. So now it's relatively easy to observe chemistry in disks around really low mass stars, right? And so here are some results from the MINDS team where they find this extremely high abundances, extremely high column densities of complex organic chemistry in very, very little water, right? It's indication of a carbon to oxygen ratio in the inner disk that is significantly higher than 1, right? So you see not just acetylene C2H2, you see benzene, you see longer chains, both aromatics and aliphatics in these regions here, and it's so much it becomes very optically thick actually, and you get these pseudo continuum of organics in these disks. Another thing we see, though, it's also interesting, is so the example I showed before is this was a disk around a very young star. We see a similar thing in disks around not just lower mass stars, but also higher mass, or not high mass stars, but not quite as low mass, but around stars that are much older, right? And so here's an example from Feng Long's program, gas in disks that are tens of millions of years old. It's actually kind of hard to understand how these primordial disks still persist, but they do. In some cases, they're called Peter Pan disks, right, because they're forever young. But these are nearly always characterized by this similar, very, very high carbon to oxygen ratio, dominated by organics and with very little water. And so you plot the samples up now here, and you have these two effects. So on the left-hand side here, there's an example of a disk. It's from the Mines survey, showing that there is a separation in luminosity, as we mentioned before. So this is a proxy for stellar mass, of the acetylene to water ratio, where disks around very low luminosity, low mass stars have a much higher organic to oxygen ratio. And on the right-hand side is from Feng Long's paper, showing that there is an apparent increase in the carbon to oxygen ratio as a function of age, right? So there's a real potential evolutionary effect here. And again, what we think is happening potentially is that we have these competing timescales, right? Of pebble drift that enriches the oxygen over time, up until a certain time, and then the oxygen is depleted again when you get to very old ages. And then you have an enrichment of carbon that potentially comes from a very slow erosion of carbon-rich, very refractory dust grains, on a much longer time scale. And so over time, that increases the carbon to oxygen ratio here. So these different effects that we're trying to disentangle with JWST at the moment here, but very exciting kind of thing. And you can imagine that again, depending on if these planets are forming, when these disks are forming planets, depending on where and when the planets are forming, you can end up with very different composition of planets, right? And so it becomes very important to understand these chemical effects. All right, so it's been a long talk here about JWST here. I want to get to PRIMA here. So what are we doing here? So JWST has produces amazing data, but it's limited. It's limited in wavelength range, and it's limited in spectral resolving power. So the wavelength range is limited out to about 28 micron. And so if you plot that on top of the distribution of water lines that I showed before, you see that we don't actually have access all the way out to the snow line with JWST. Right, the lowest lying upper level energy of a water line with JWST sits at 800 Kelvin. That gives access to water vapor that's about, maybe down to 300, 250 Kelvin. When the water snow line is at 150 Kelvin, we don't actually quite get that. We need access to longer wavelengths to measure the water vapor distribution out to the snow line, at the snow line, and beyond the snow line. And so this is the most critical region, really, for understanding the chemistry of most planets, right? If you're thinking they're forming just at the snow line or just outside the snow line, in particular for giant planets. And so getting access to that is one of the key objectives with PRIMA, right? So getting us access to wavelengths longer than 28 micron. And so that's exactly what we get here. So here's, of course, a simulation of a protoplanetary disk with PRIMA. This is a simulation that is based directly off of what we see with JWST, right? So it matches the water lines and other components that's already detected with JWST, and actually with a couple of cases with Herschel as well. And so you see the strength of all the water lines throughout the PRIMA range. We also, of course, get access to water ice. So we get both the vapor and the ice. The water ice we see through an emission through these far-infrared bands here, and they're unique in the sense that, yes, there's water ice seen at shorter wavelengths, but that is only seen in absorption, so you need a special kind of geometry in order to see it, and they're poor mass tracers. The reason we can see water ice in emission and at far infrared wavelengths is that you excite those emission lines at temperatures that are cooler than the freeze-out temperature, whereas the shorter wavelength lines, I can take, for example, a 3-micron water ice band. In order to excite that emission, you have to heat the dust grains to temperatures much higher than the ice sublimation. And so that's why we just never see that in absorption. So the water ice you get here in the far infrared with PRIMA is an actual mass tracer. And we get access to also the hydrogen deuterate line at 112 micron, which is the best tracer of the total H2 total H2 gas mass in disks. And so here's a schematic of that as well here. So what we can do here with PRIMA is, whereas JWST gives access to JWST gives us access to the warm water, the hot water. So you can see that on the red and the yellow here. PRIMA gives us access to the 150 Kelvin water at the snow line, and also the cold water at 50 Kelvin, which we think is produced by photodesorption from icy grain mantles. So where we have the biggest effect in terms of difference between icy pebble drift and no icy pebble drift is at the snow line here. So you can see that in the green and the purple line. So we see a little bit of a difference there in JWST, and we see a lot of indications that this is happening, but we expect once we have access to the far infrared, we should see a much, much bigger difference between different theoretical simulations of that include pebble drift. And so we think that can really constrain what is going on in disks. Here's some more detailed simulations of protoplanetary disk as of PRIMA. Another important point is that if I draw your attention to the lower left panel here, we have overlap with MIRI, with PRIMA, but with the high resolution mode of PRIMA, we have about 10 times the resolving power of MIRI at about the same sensitivity here. So we can actually not only measure the line fluxes of all these lines, we can also kinematically resolve them in this wavelength here. And so kinematically resolving the water lines using a Keplerian disk model gives us a quite direct measure of the emitting area and the spatial structure of the emitting water. So just mention as well, we are getting access to the hydrogen deuteride line that gives us access to the total disk mass, in particular in combination with other measurements like CO observations with ALMA that gives us access to the temperature of the HD. So you combine the HD line flux observed with PRIMA with the gas temperature as traced by CO, and you end up with a fairly precise measurement of the disk masses to within maybe 30% or something like that is what we think we can get to. Why are we talking about disk masses here as well? Well, we are interested in measuring the abundances of the volatile elements, but not just the carbon to oxygen ratio, but also the absolute abundances. So the carbon relative, for example, carbon relative to hydrogen, the oxygen relative to hydrogen. So this sort of just a summary of where we get all the components from, right? So imagine we're getting access to the carbon chemistry with JWST, organics with ALMA, CO, C measurements. From PRIMA, we are getting access to the total amount of hydrogen through the HD observations. We're getting access to the total oxygen through PRIMA water. We put all those together, we get the carbon to hydrogen, we get the oxygen to hydrogen. We put those together, we get the carbon to oxygen as well. And we get all of that as a function of radius in the disk. And so that allows for a large sample of disks. And so that allows us to finally compare the abundances that we see in mature planetary systems with the formation, the abundances at the time of formation of planets throughout the disk, inside, at the snow line, and across the snow line. So that's a basic story. So just in summary, we ask what is the probability of at least the availability of life-giving elements in planet-forming regions. We now know this is nearly 100% in disks around solar mass stars in the first couple of million years. What is the relative abundance of these elements? We know that it's highly dependent on both stellar mass and time. And we really need to map that out relative to when planets form, because it's probably something that will give rise to very different compositions of planetary systems. And PRIMA is really required to measure the elemental abundances across the planet-forming regions. So with that, I'll thank you for your attention. I'm happy to take questions.
All right, thanks, Klaus. And we can go ahead and take questions from the audience. You can raise your hand or put a question in the chat if you'd like. Doug, go ahead.
So Klaus, thank you for that. That was an excellent talk. You gave it from the perspective that we really understand what's going on and that we have a really good story at the moment for what's going on. And so we can now try to measure things and get further. I was curious whether you could mention at all any places where you think there are real uncertainties or where we may find gotchas that in fact our story isn't. We're both old enough to have remembered that these stories have changed a lot over the years as suddenly pebble accretion becomes important or this becomes important. So just wondering whether you could riff a little on what else might be out there for us to be looking at rather than tying up the story.
Yeah, thanks, Doug. Yeah, no, I definitely don't think we have a full story for this here. It's a lot of issues. What we do have is we have an observation of real strong effects, right? There's observational effects that we need to explain. That in itself is, to me, a big advance. Or it's actually when JWST came out, I was worried that it was just going to be all a random mess, right? But it's not. It's not. There's some really strong effects that we have to explain. The pebble drift and the carbon to oxygen ratio is actually, there's a lot of disagreement, let's say, in the models, right? Because when you drift pebbles in, it's not obvious how that changes the oxygen rates because you're bringing a lot of water, but at the same time, you're bringing a lot of other things, right? So I think the devil is in the details there of understanding how you can get these very dramatic carbon to oxygen ratios, right? And we're not talking small differences in order to get these very quite crazy, actually, organic abundances. People are talking about carbon to oxygen ratio of not just a few, right, but orders of magnitude. Very strange very strange gas to dust ratios as well. And so I think we're really just starting out building the theoretical tools that we need to fully understand this, but we have a great observational data set, so that's all good news. Okay, any other questions?
All right, well, if we don't have questions, we will thank Klaus again. So thank you so much for this excellent talk. Oh, we do have another question. So Hendrik is asking, is there anything to be learned from unresolved far infrared polarimetry, I believe? Polarimetry.
Yeah. Yes, I'm certain there is. It's not something we actually have looked at very carefully for disks. I mean, you'll get 4 polarimetric points for a disk. My guess is it's going to be a bit difficult to interpret when they're unresolved. It would be ideal to get resolved images, especially because you have sort of circular structures, right, and how they how they conspire to blend things up might be a bit difficult to. But it's a good question. It's probably something that it's a question we should ask and see if there is something, since we're getting it for free, essentially, almost.
Wonderful. Well, thank you again, Klaus. Thank you again, everyone, for attending. And just a reminder that we will return again to our regularly scheduled talk in 2 weeks. All right. Thank you.
Thanks, everyone.